Well, we had great success in dealing with the geometric series. But now the going gets tough, in that for most infinite series, there is no concise formula for the partial sums. So we have to approach the issue of convergence, that is, whether the series makes sense, from the standpoint of proving or disproving convergence without being able to actually tell you the value of the sum. Weird, but that's all we can do. First of all, we need to introduce systematic and clear notation and definitions. We will denote an infinite series by an infinite summation. Summation k equals 0 to infinity of ak, or summation n equals 1 to infinity of bn, for example, where the ak and bn are assumed to be given sequences of numbers which we are trying to add. The point is that we can use any symbolism for the given sequence, and we can use any symbol for the summation variable. In this case, we used k in the first sum and n in the second. Furthermore, we can start the sum at any specific value of the summation index. In our example, we started k at 0, but we started n at 1. Here are some examples to show you the versatility of the notation. Summation k equals 3 to infinity of log k divided by k squared. So that's just log 3 over 3 squared, plus log 4 over 4 squared, plus log 5 over 5 squared, and so on. Summation s equals minus 2 to infinity of 3 times the sine of s pi. That's 3 times the sine of minus 2 pi, plus 3 times the sine of minus 1 times pi, plus 3 times the sine of 0 times pi, plus 3 times the sine of 1 times pi, and so on, forever. Can you see that this last series sums to 0? Our only rigidly fixed rule is that the sum must not end, i.e. the upper limit of the sum must be the symbol infinity. The next stage is to develop notation for the partial sums. Various texts use different symbols. I will use s subscript n for the summation k equals 0 to n of ak, or capital S subscript capital N equal to the summation n equal 1 to capital N of b subscript n. So when my summation index is k, my partial sum will be capital S subscript n, and it will end at the natural number n. If the summation index is n, as it is in many texts, then we use capital N for the upper limit of summation to form the partial sum, and it's denoted capital S subscript capital N. The lower limit of the partial sum can be whatever we have chosen. I just put in 0 and 1 as examples. Here's an example of the creation of the sequence of partial sums. Suppose we are dealing with the series summation k equals 3 to infinity of log k over k squared. Then the sequence of partial sums starts with S3, since the series starts with k equals 3. S3 is the sum from k equals 3 to 3 of log k over k squared, which is the single term log 3 over 3 squared. S4 would be the sum from k equals 3 to 4 of log k over k squared. That's log 3 over 3 squared plus log 4 over 4 squared. And now you see how we proceed. S5 would be the sum from k equals 3 to 5, and that would be log 3 over 3 squared plus log 4 over 4 squared plus log 5 over 5 squared. I hope you can see how simple and sensible is this notation. It is basically a simple algorithm for generating successively longer sums, which we hope will tell us what is happening as we add more and more terms. Notice also that we really don't care about the value of the first million partial sums. It is only the limit of these sums that matters. Now we want to establish two fundamental results. The first says that you can change any finite set of terms in an infinite series, and that change will not affect the convergence of the series. Of course, the actual sum will be different. As an example, we know that the geometric series, summation 1 over 3 to the k, sums exactly to 3 halves. So we know the series converges, and we have actually computed the sum. Now suppose that someone changes the first 3 terms of this series and asks you whether the new series converges. For example, they hand you the series 2 plus 6 plus 1 over 4 squared plus the summation from k equal 3 to infinity of 1 over 3 to the k. Or writing it out, the new series is 2 plus 6 plus 1 over 4 squared, and then you start the geometric progression 1 over 3 cubed, 1 over 3 to the 4th, and so on. Now just factor 1 over 3 to the 4th out of the terms where this factor appears, and recognize that you end up with the geometric series again. Strange, but very typical of what happens when dealing with infinite sums. You get 2 plus 6 plus 1 over 4 squared sitting out front, and then you get, added to it, 1 over 3 cubed, factored out, times the geometric series, 1 plus 1/3 plus 1 over 3 squared, and so on, forever. And that's just exactly 2 plus 6 plus 1 over 4 squared, plus the factor 1 over 3 cubed, times the sum of the geometric series, 1 over 1 minus 1/3. In short, by recognizing the geometric series embedded in the new series, we can actually sum the new series. The point of our principle is that even if we can't carry out a nice observation like this, we do know that the new series will either diverge or converge the same as the old series, of course to a different sum in general. In our example, the original geometric series summed to 3/2, while the new series sums to 8 plus 1/16 plus 1/27 times 3/2. I want to state and prove a particularly important form of this principle, which is called the equivalent sequence theorem in the notes. The theorem goes as follows. Given a series, summation k equal 1 to infinity ak, suppose we replace the first p terms, a1 through ap, with new terms, b1 through bp. Then the new series, b1 plus b2 plus bp plus ap plus 1 plus ap plus 2, and so on, will converge if and only if the original series converges. It will diverge if and only if the original series diverges. For the proof, label the partial sums of the two series as follows. Sn will be the partial sum k equal 1 to n of the ak's. Tn will be the nth partial sum of the new series. That's b1 plus b2 and so on up to bp, plus the sum from p plus 1 to n of the ak's. And we always choose n bigger than p so everything makes sense. Now notice that Tn is just Sn with a1 through ap subtracted off and b1 plus bp added in. Now take the limit as n tends to infinity of this identity between Tn and Sn. And remember that the limit of a sum is the sum of the limits, and the limit of a constant is just the constant itself. So the limit of the sequence Tn is exactly equal to the limit of the sequence Sn when they both exist. Well, with the subtraction of a1 through ap and addition of b1 through bp on the right. More precisely, the limit on the left exists if and only if the limit on the right exists, which is exactly what we wanted to prove. The next principle we want to state and prove is a first result which allows us to assert that a sum does not make sense. The theorem goes as follows. If the series summation k equal 1 to infinity of ak converges, then we must have the limit as k tends to infinity of ak is 0. In plain English, the things you are adding up must get smaller and approach 0 if you want any chance of the series converging. This theorem does not assert that if the limit is 0 of the ak's, then the series converges. What it does say is if that limit does not exist or is different from 0, then the series cannot converge. As an example, consider the series summation k equal 1 to infinity of minus 1 to the k times the logarithm of k. That's log 2 minus log 3 plus log 4 minus log 5, and so on. The log 1 term disappeared because log of 1 is 0. Since the limit as k tends to infinity of minus 1 to the k log k does not exist, That's because the values of this sequence oscillate between ever larger positive and negative numbers. We know the original series cannot converge. For a second and very important example, consider the harmonic series, named by the ancient Greeks for its connection to musical frequencies. That's the summation from k equal 1 to infinity of the reciprocals of the natural numbers, in other words, 1 over k. So the series consists of the sum 1 plus a half plus a third plus a quarter, and so on. You can see immediately that the limit of the AKs, which is just the limit of 1 over k, is 0. In this case, the theorem tells us nothing, because the theorem only asserts that if the series converges, then the limit of the AKs must be 0. In the language of mathematical logic, the condition limit as k goes to infinity of ak equals 0 is necessary but not sufficient for the convergence of the series. Surprisingly, at least to most people, this series does not converge. In fact, the partial sums get larger and larger without bound, so we say that the series diverges to plus infinity, even though the limit of the AKs is 0. The proof depends on a simple observation from arithmetic. Given any natural number p, if I add up the reciprocals of natural numbers from 1 over p to 1 over twice p, the sum will always exceed 1/2. For example, for p equal 2, twice p is 4, so you add up the reciprocals, 1/2 plus 1/3 plus 1/4, stopping at 1 over 2p. That's 13/12, and that's certainly bigger than a half. For p equals 5, 2p is 10, so I add up all the reciprocals between 1 over 5 and 1 over 10, reciprocals of natural numbers. And when you do that, you get 21/31 divided by 25/20, which is still much bigger than a half. In general, when you add up 1 over k, starting with k equals p and stopping at k equals 2p, you have 1 over p plus 1 over p plus 1, and so on, up to 1 over twice p. Now comes a simple observation. Every term in this sum is bigger than or equal to 1 over 2p, because this is the smallest term in the sum. Notice also that there are p plus 1 terms in this sum, since we started with 1 over p plus 0, and we stopped with 1 over p plus p. So the sum is larger than we would get if we had added up the number 1 over 2p, a total of p plus 1 times. In other words, summation from p to 2p of 1 over k, that's 1 over p plus 1 over p plus 1, up to and including 1 over 2p. That number exceeds p plus 1 times 1 over 2p. And now you rearrange that product of fractions and write it as p plus 1 over p times a half. P plus 1 over p is bigger than 1, so that product is bigger than a half. It is this simple observation that allows us to conclude that the harmonic series makes no sense, i.e. it diverges. We just write this series in terms of a collection that never ends of finite sums from 1 over p to 1 over 2p. So we have summation k equal 1 to infinity of 1 over k. That begins with the ratio 1 over 1. p is 1, 2p is 2, so we bracket the sum 1 over 1 plus 1 over 2. Now we start the next term in the series, that would be 1 over 3, and that has p equal 3, 2p is 6. So we take the reciprocals 1 over k, starting with 1 over 3 and stopping with 1 over 6. We bracket that. Now we go to the next term in our series, 1 over 7. That sets p equal to 7. 2p is 14. We bracket and add the numbers from 1 over 7 to 1 over 14. Our next term is 1 over 15. p 15. 2p is 30. We write out the reciprocals, 1 over 15, 1 over 16, and so on up to 1 over 30. And we bracket that sum. And you see that we can go on this way forever, and every one of these finite sums exceeds 1/2. So the partial sums must just keep getting larger and larger without bound, and so the harmonic series diverges to plus infinity. One final observation. If summation k equals 0 to infinity of ak and summation k equals 0 to infinity of bk both converge, then for any constants alpha and beta, the sum from k equal 1 to infinity of the combined series alpha ak plus beta bk is equal to alpha times summation k equal 1 to infinity of the ak's plus beta times summation k equal 1 to infinity of the bk's. In other words, in large part, convergent series behave just like finite sums. For example, the summation k equals 0 to infinity of 5 times 1/3 to the k plus 3 times 2/5 to the k is the same as 5 times summation k equals 0 to infinity of 1/3 to the k plus 3 times summation k equals 0 to infinity 2/5 to the k. And that's the same as 5 times the ratio 1 over 1 minus 1/3 plus 3 times the ratio 1 over 1 minus 2/5, and that reduces to the fraction 25 over 2.